if we would know that for which values of q it converges, then we could use this formula and we would have the answer immediately. Yeah. So this is quite useful, but we are not done yet, and we should never forget about this this condition that the series has to converges. Otherwise, this is completely nonsense thing. So, for example, we could like use the same approach to some of the arithmetic series like this. So, if this would be equal q, yeah. So then what we can do is to take q. Okay. And for example, we can do like multiply it by 2, and we would obtain like we would obtain 2 plus 4 plus 6 plus 8 plus 10 and so on. So this is definitely larger than 2 plus 3 plus 4 and so on. So this is definitely larger than x minus 1, meaning that x is larger than minus 1/2. Okay, this works, but yeah, maybe better counterexample is 1 plus 2 plus 4 plus 8 and so on, like the geometric series for q equal 2. Yeah. And from our previous formula, we would obtain that this sum is equal 1 over 1 minus 2, meaning minus 1. Which is nonsense, because we are summing some non-negative numbers which are growing faster and faster. So this can be minus 1, this is plus infinity, of course. Yeah, so we need to check whether the series converges or diverges. And now we can do it in many different ways. So probably the simplest way how to derive that is from a finite geometric series, meaning just sum a0 plus a1 and so on to an. So maybe you know the formula for this, or we can derive it. So we have series 1 plus q squared plus q cubed and so on to q to n, and so what we can do is we can like take this whole thing and write it once again and multiply it by q. But this is nothing else than q plus q squared plus q cubed and so on plus q to n plus q to n plus 1. But now if we take a difference of these two quantities, then what we obtain is this was equal q, this was equal x, then we have x minus q times x is nothing else than 1 minus q to n plus 1, because all other terms will be eliminated there at the top and the bottom part, so they will eliminate each other. So we have just this, meaning that x is nothing else than 1 minus q to n plus 1 over 1 minus q. Okay, so this is our formula we want. So now what we know that Sn, partial sum for the geometric series, is equal to 1 minus q to n plus 1 over 1 minus q. And the question before was what is the limit for n going to infinity of Sn. Yeah, so what is limit for n going to infinity of 1 minus q to plus 1 over 1 minus q. So this thing down here is just constant, and now the only thing which it depends on is the value of q. So if like the absolute, and we can consider the absolute value here, like we are just considering like the geometric series for the like positive terms, but we could like solve it in general. So if we consider if the absolute value of q is at most 1, then what it says that this thing, when the n is larger and larger, this goes to 0, meaning that this is going closer and closer to 1 over 1 minus q, which is the final sum we wanted, and this is a final number. Now if q is equal plus or minus 1, then like the thing we obtain here is like if q is equal 1, then this doesn't make any sense, because we are like dividing by 0. So like our previous derivation was actually incorrect. We would obtain some different derivation. So anyway, it would tend to plus infinity, and if q is minus 1, then it's the case that we have plus and minus 1 in like changing order, like alternating plus minus 1 plus 1 minus 1 and so on. And we already discussed that the sum does not exist. Yeah, because like the sequence of partial sums will be always 1 0 1 0 1 0, and the limit here does not exist. So the last case is if the q is larger than 1, and in such a case this thing here will blow up, become larger and larger, and therefore this sum will be either will not exist if like if the q is negative, then it will always like the sign will alternate in the limit, or it will be equal infinity, so then it diverges. So we know that for q is more than 1 it converges, and otherwise it diverges. Okay, so we can state it as like our first result. So a geometric series converges if and only if absolute value of q is at most smaller than 1. So now we were able to somewhat characterize all geometric series, and this is like our basic tool we are going to use today. So what we would like to do is using geometric series to be able to decide whether some other more complicated series converge or diverge, and we can use the following idea based on comparing series. Like imagine the following: we have a series an, and we have another series bn, yeah, and all the numbers an and bn are positive or non-negative, and now what we know is that bn converges, and also we know that bn is larger than an, and maybe everywhere or almost everywhere, meaning there can be a few exceptions. So this clearly implies that also sum of an converges, since basically this gives us some kind of comparison between partial sums, and so we can use some kind of like property of limits, or we can just see why it holds. Yeah, and similarly, if sum an diverges, yeah, and again an is smaller than bn, then on the other hand bn diverges. So if we would like to prove that some series diverges or converges, we just have to find some another appropriate series, and we are basically done. Yeah, and we don't need exactly smaller here. We, for example, if 2 times an would be still smaller than bn, or 1/2 of an would be still smaller than bn, or whatever relation like this would hold, then we can use it anyway. So if an is somewhat, we could write it like this: is like the values of an are dominated by bn, then a similar thing will hold, that bn converges implies an converges. Now also, if an has the similar or the same values, or almost the same values as bn, then both of the series are either converging or diverging. So both of the so we just need to find out how one of the series is behaving. So once again we can define these comparisons using limits. So what we are going to do, we are going to look at the limit for n tending to infinity of an over bn, and as we know from the before, this is comparing how large is one sequence growing compared to the other sequence. And so basically what we are doing here, that if this thing here is equal to constant, then an is roughly bn, yeah, times the constant c. So meaning that an converges if and only if bn converges, like this. And if this limit is equal 0, what does hold that an is much smaller than bn. Bn is larger and larger, and it will beat an. So meaning that bn is larger, so if bn is converging, then an converges too. And on the other hand, if an is diverging, then bn is also diverging, and so on. If similar, if this thing here is in infinity. So basically, using